Hello, welcome to this third lecture on week number 3 on radio astronomy. We are talking about antenna theory and other fundamentals. So we have mostly covered in this particular week details about radio antenna, why it is important, studied with an ideal Hertz dipole radiation pattern, the measurement of the electric and magnetic field at different distances from the antenna, how do we calculate radiation pattern, far field radiation pattern, what are different parameters of a radiation pattern, half power beam width, first null beam width, and directivity, radiation impedances, etc. So in this particular lecture, we will carry that discussion onward with mostly discussing about the impedances and also solving some problems which will help you to understand what is going on. So the next thing is polarization. Polarization of an antenna in a given direction is defined as the polarization of the wave transmitted or radiated by the antenna. Polarization of radiated wave is defined as a property of the electromagnetic wave describing the time varying direction and relative magnitude of the electric field vector. Specifically, the figure traced as a function of time by the extremity of the vector at a fixed location in space and the sense in which it is traced as observed along the direction of propagation. The polarization characteristics of an antenna can be represented by its polarization pattern, which is the spatial distribution of the polarizations of a field vector by an antenna over its radiation sphere. So as the wave propagates, the polarization vector will make a motion, and that defines the polarization pattern of the antenna. One thing we have to understand here, and we will talk about it more, is for radio astronomy, when we are mostly receiving the radiation from the cosmos, the radiation itself can be polarized. Okay, an antenna itself, by its characteristics, also have a polarization property. Now, this too has to be disentangled to understand the inherent radiation, the polarization property of the radiation coming from the cosmos itself. We will talk about it little bit when we come, but this has to be, nevertheless, you please note it down that this has to be done when you actually analyze. Otherwise, you will get a wrong answer, or measurement of the polarization of the source which you are observing in the far field sky will become erroneous. So the next important parameter to discuss will be input impedance. We started a little bit, and this is mostly for completeness of the discussion that we are going into this. It is defined as impedance present by an antenna at its terminals, or the ratio of the voltage to current at a pair of terminals, or the ratio of the appropriate components of the electric to magnetic fields at a given point. Now, typically it is a generator, and you see a transmission line ending up into an antenna. Okay, if you try to draw a equivalent circuit, Thevenin equivalent circuit, the generator of the voltage can be divided into its voltage, its resistance, and reactance. And similarly, there is a load resistance and the radiation resistance is there. And the reactive part. Okay, so the antenna impedance can be broken up into this R sub R and X sub A. There is a RL, which is another load resistance. So we can break this up into this format by following the Thevenin equivalent circuit. If you have already done it, fantastic. I will follow this. Otherwise, just note it down, and we can discuss it more later, most likely. So these terminals between so the impedance is measured between the terminals A and B in this particular figure, and where the antenna impedance is defined by Z sub A is RA plus J into XA, where ZA is the antenna impedance and RA is the antenna resistance, XA is the reactance between terminals A and B. In general, resistive part consists of two components. RA is R sub R and R sub L. R sub R is the radiation resistance and R sub L is the loss resistance of the antenna. And if we assume that the antenna is attached to a generator with the internal impedance of Z sub G, then there is a R sub G and X sub G of the voltage source itself. Hence, to find the amount of power delivered to R sub R, the radiation resistance for radiation, and the amount of dissipated in R sub L, the loss resistance as heat or the ohmic loss, I square RL over T, we apply Kirchhoff's voltage law in circuit showing in B. Okay, so this Kirchhoff's voltage law is applied, and I sub G can be written in terms of VG over ZA and ZG. So after this solving for the power, we get the power radiated by the antenna and the power dissipated by heat at the antenna due to the internal resistance RG is given by this expression. Okay. Now, by following something called a maximum power transfer theorem, it appears that the impedance of this internal voltage source and the impedance of the antenna, they should be conjugate of each other to be able to do the maximum power transfer. What it means is that the resistive part R sub R plus R sub L should be equal to RG, and the XA should be negative of XG. Okay, that's how it becomes conjugate, right? Because it's complex in nature. Thus, when the maximum power transfer is delivered, the power radiated or lost in the heat will be given by this Vg square over 8 RR over RR plus RL whole square. Okay, and PL is given by Vg square over 8 and RL over RL plus RR whole square, and Pg is given by this Vg square over 8 Rg. So here Pg is equal to PR plus PL. That is the total power generated by the generator and dissipated as heat and radiated finally. So this is the maximum you can get if everything is matched. Quite valuable to note, because you sometimes have a budget of radiated power, particularly in case of transmission, the communication. There is a power radiated and it has to be matched with, because it has to go over a long distance, etc., etc. For remote sensing also, this radiated power has a valuation. For radars, atmospheric radars, Doppler radars, this power has a value. So this maximum power transfer theorem, it has to be applied, and the design of the internal circuitry, etc., has to be done properly to maintain this. For radio astronomy, it also is important, because finally it is going to we already have a very less amount of signals coming in from the cosmic sources, and we don't want to lose any of them. Okay, so what happens is that if we match the internal impedances, in case of us, it's in the receiving mode. So it's not a generator; it's a receiver, which is followed, and so receiver impedance has to be matched with the antenna impedance. Otherwise, there will be some amount of signal will be reflected back. Okay, so we do not want to do that also. So this particular analysis is extremely important while designing an antenna, whether in a transmit mode or a receive mode. Okay, thing to note here is that in the power by the generator, half is dissipated as heat due to its internal resistance, and other half is delivered to the antenna if and only if we have a conjugate matching. The power that is delivered to the antenna, a part of that is radiated through the mechanism provided by radiation resistance, and the other is dissipated as heat, which influences part of the overall efficiency of the antenna. If antenna is lossless and matched to the transmission line, that is not equal to 1, then half of the total power supplied by the generator is radiated by the antenna itself. So if we consider the inverse case where antenna is acting as a receiver, as we just mentioned, then in similar way we will arrive at the following terms, showcasing the power of matching impedances. Okay. Antenna radiation efficiency, we have already discussed it. The conduction dielectric efficiency, ECD, is defined as a ratio of the power delivered to the radiation resistance to the power delivered to RR and RL. Okay, that is the ECD. We mentioned it briefly in the last lecture. Here we define it. Okay. If we consider a metal rod of length L and a uniform cross section of area of A, the DC resistance is given by L over sigma A and having a skin depth of delta. Then the high frequency resistance can be written in terms of these values. So high frequency resistance is coming out to be L over P root over of omega mu naught over 2 sigma. P is the perimeter of the cross section, and RS is the conductor surface resistance. Omega is the angular frequency, and omega mu naught is the permeability of free space. Sigma is the conductivity of the metal. The high frequency resistance can in turn provide the RL based on the current distribution in the antenna. So that was the radiation efficiency and the dielectric efficiency particularly. Next term we concentrate on is the antenna effective length and equivalent area. So antenna has different geometry. So to come up with an effective length, if it is like a bucket, then the effective area is understandable. But if it is like simply like dipoles, what is the effective area and as such? So this is actually important. So what we start off is that define a quantity called vector effective length L sub E for an antenna, which is kind of a complex vector quantity and is represented by LE theta phi is given by A theta, L theta and A phi, L phi, where L theta and L phi are the length of the antenna along theta and phi directions, of course. Now in the far field quantity, it is related to the L is also referred to as an effective height in some sense. Okay, it is a far field quantity and it is related to the far field electric field radiated by the antenna with the current I in its terminals. So you can write the E sub A in form of that. That will give rise to the open circuit voltage value in terms of effective length and the E. Additionally, we see there is a number of equivalent areas associated with an antenna. One of those equivalent areas is an effective area or aperture area and is defined as the ratio of the available power at the terminals of a receiving antenna to the power flux density of a plane wave incident on the antenna from that direction. The wave being polarization matched to the antenna. Okay, if the direction is not specified, the direction of the maximum radiation intensity is implied. So the effective area is the power flux density of the incident wave over the radiation density. Okay, so that gives you this expression. So W is the power density of the incident wave and PT is the power delivered to the load of this incident wave, and effective area is given by A sub E. Using total power generated by the antenna in reception mode as discussed, when we are discussing the antenna impedance, we get the effective area to be given by this. So there are various ways of defining this effective area. One, by the power transmitted to the load, and another one is in the reception mode, the power generated, okay, by the antenna. Both of them can be used to define the effective area. So maximum effective, if we consider maximum power transfer condition, then the maximum effective area can be reached by following the maximum power transfer conditions, where the source voltage, the source impedance or the voltage source impedance has to match with the antenna impedance in conjugation. So there are several other definitions, like scattering area can be also defined as the equivalent area given by this formula. There is loss area can also be given, capture area can also be written. So it can be observed that the captured area, which is the equivalent area which when multiplied by the incident power density leads to total power captured. Okay. The capture area is like effective area plus scattering area plus loss area. So it is a superset kind of a thing. Now we define a term called aperture efficiency, which is defined as the ratio of the maximum effective area of the antenna to the physical area. Okay. So this maximum effective area is kind of linked to the maximum power transfer. So basically the efficiency, okay, to the physical. So physical area is a measure of the antenna, like if you have a dish, the dish diameter is known, so you can calculate the area of the dish. And the magnetically, that doesn't really matter. What matters is that maximum effective area. Okay, so this ratio kind of gives you an efficiency of the aperture, which is radiating or receiving. For aperture type antennas such as waveguides, horns and reflectors, the maximum effective area cannot exceed the physical area, but it can be equal to it. So it cannot be higher than the aperture in the physical aperture area, but it can be less than or equal to that. That means the maximum efficiency cannot be exceeding 100%, which is unphysical. Further, one can introduce another area called partial effective area of an antenna for a given polarization in each direction. So for any given polarization, you can define a term of partial effective area, because which is sensitive to that particular polarization. So that brings us to the close of all the definition of this, all the parameters which are involved in this. So here what we do is we summarize a bunch of parameters which are important for our discussion henceforth. These first two we haven't yet come, which is just here for completion, but the next bunch of the details are actually, many of them we have actually gone through. This is just for completeness and for your reference. It will be part of the lecture material distributed. So that is a summary of all the things. We will come back to this too in the next few lectures. Before we proceed further, I think there are a lot of material we have covered, so I think it's time to go through a few sample questions, and so that you can understand the concepts more clearly. So first one we are taking, for a sphere of radius r, find the solid angle omega a in square radians or steradians of a spherical cap on the surface of the sphere over the North Pole region, defined by spherical angles theta 0 to 30 degree and phi 0 to 360 degree. Find the solid angle. A exactly, B using omega A is equal to delta theta 1 times delta theta 2, where delta theta and delta theta 2 are two perpendicular angular separations of the spherical cap passing through the North Pole. Compare between the two. So for the first one, we use the formula. The steradian, the infinitesimal solid angle, is defined by the area over r square. That is given according to the spherical coordinate, because dA is r square sine theta d theta d phi. So r square cancels. So this becomes d omega becomes sine theta d theta d phi. So we can write omega A is equal to the double integral of d omega, and that can be written in terms of 0.83566. That's in radian. Okay, by using approximation, we get omega A is equal to delta theta 1 times delta theta 2. If they were same, then it becomes delta theta 1 whole square, and that gives you 1.09662. So by this approximation, if you follow these approximation rules which we have defined earlier, then this directivity can have an error of or approximate beam solid angle can have an error up to 31%, which is quite high. Coming to question number 2, the radial component of the radiated power density of an antenna is given by omega W rad is equal to AR unit vector times W sub R, given by A naught sine theta over R square watt per meter square, where A0 is the peak value of the power density, theta is the usual spherical coordinate, and AR is a radial unit vector. Define total radiated power. Total radiated power is given by this double integral of W rad dot n, the direction normal to the surface area, and times dA. So if you do that simple expression, and you can, so a three-dimensional, that is equal to pi square A naught. So a three-dimensional normalized plot of the average power density at a distance of r equal to 1. The radial, question number 3, is radial component of the radiated power for given this thing is also given by, just a second, this is also, yeah, they are similar looking. So A0 is the peak value of the power density, theta is the usual spherical coordinate, and AR is the radial unit vector. Determine the radiation intensity, and using the relationship of radiation intensity and total power, determine the total power. So it's the same setup. So U is the intensity, is R square times W rad. So that is equal to A0 sine theta, because you have W rad is equal to A0 sine theta over R square. So R square cancels off, this is the thing. So P rad is double integral of U sine theta d theta d phi, which is given by pi square A0. Now question number 4, the normalized radiation intensity of an antenna is presented by U theta is given by cosine square theta and cosine square 3 theta, where theta goes from 0 to 90 degree and phi from 0 to 360 degree. The 3 and 2 dimensional plots of this is plotted in a linear scale and are shown in the left. Okay. Now what is to be found? Please calculate the half power beam width in radians and degrees, and F and BW, or the first null beam width, in radians and degrees. Okay. So U theta is given, you calculate HPBW and F and BW. So from U theta, represents the power pattern. To find half power beam width, you set the function equal to half of its maximum value. Okay, and you finally find the theta h equal to this, where ultimately you can calculate it's an equation with a transcendental function. It can be solved iteratively. After a few iterations, you can find theta h to be equal to 0.25 radians, okay, or 14.325 degree. Since the function u theta is symmetrical about maximum at theta equal to 0, then the HPBW is twice of this theta h. Okay. This that is the first one. The second one is to find the first null beam width. So to set that u theta has to be equal to 0 at the first null. So if you do that, then this equal to 0, then theta n can be solved as theta can be 90 degree, and 3 theta n can also be 30 degree. So for both these two values, 30 degree and 90 degree, this particular beam pattern goes to 0. So there are two solutions for theta n. Okay. However, because it is the first null, so the first null will happen at the smallest value of theta, right? Because there are 2 theta and this is the first null. So first null will be at 30 degree, not 90 degree. Hence, one side is 30 degree for symmetry, the other side is also 30 degree, and so that becomes, the FNBW becomes twice of theta n, which is equal to 60 degree. Okay. Let me go through it once more. So we have been given a u theta, and we have to calculate the half power beam width and the full first null beam width. So half power beam width is the place where the power becomes half of its maximum value. Okay, so that means the maximum value is where is 1 cosine square theta and cosine square 3 theta. This value is 1, maximum value is 1 of this function. So half of it is 0.5. So you basically then 0.5, you take a square root of that and then finally find that 0.707 is equal to the cosine theta h and cosine 3 theta h. So that gives you to a theta h which is also a function of theta h. Basically these are called transcendental functions. Finally, after solving this iteratively, you get it is equal to the 14.325 degree. Okay. After that, if you go and find the first, so 14.325 degree is towards the half. The other half has to be also calculated, right? So this is the, from one side you're coming down to the 0.5. From the other side also you have to come down to 0.5, and the distance between the two half points is the half power beam width. So it's effectively it is twice of this theta h is the half power beam width, which is equal to 28.65 degree. That's the half power beam width. Now for this particular beam pattern, the FNBW is where the u theta comes to 0. Now u theta can be equal to 0 at 2 points, where cosine of theta is equal to 0, that is 90 degree, and cosine of 3 theta equal to 0 is theta equal to 30 degree. So because this is the first null, then the 30 degree is the value we should take. 30 degrees on the one side, so the full first null beam width will become 30 plus 30 is 60 degree. So remember, the full width half maxima is at 28.65 degree and first null beam width is at 60 degree. First null beam width is at 60 degree. Yeah. Now next question is, and as an illustration, find the maximum directivity of the antenna whose radiation intensity is that of example of question 2, which is A0 sin theta is equal to u. Write an expression of the directivity as a function of the direction angles theta and phi. So we have u as r square over w rad is A0 sin theta. Maximum radiation is directed along theta equal to pi by 2 because A0 is the maximum. So u max is A0. P rad is integral of u sin theta d theta d phi, that is equal to pi square A0. We have already calculated that. Hence the directivity d naught is 4 pi u max over p rad, that is 4 by pi or 1.27. Since the radiation intensity is only a function of theta, the directivity as a function of direction angle is represented by D equal to D naught sine theta, or 1.27 sine of theta. If it would have been sine function of phi, then the phi component will have been also included. Question number 6. The radial component of the radiated power density of an infinitesimal linear dipole of length L less than lambda, or the wavelength of radiation, is given as W average is A radial unit vector times WR, is given by A0 sine square theta by R square. A0 is the peak value, theta is the usual spherical coordinate, and AR is the unit radial vector. All these things are there. Determine the maximum directivity of an antenna and express the directivity as a function of direction angles theta and phi. So with that, this is sine square theta by R square. So almost similar to the previous, this is also function of theta only, but instead of sine theta, it becomes sine square theta. So you solve for the P rad, you get the value of A0 8 pi over 3, you get D naught is 4 pi U max over P rad, just like the previous example. If you substitute the value of P rad, you get 3 by 2 as a directivity, maximum directivity. And then you find that it is only function of sine square theta. So D also is D naught sine square theta, or 1.5 sine square theta. So that solves the problem. It's same as the previous problem, only sine theta is replaced by sine square theta. Next question, we have a radiation intensity given by U as B naught, which is the maximum value, cosine square 4. The radiation intensity exists only in the upper hemisphere, so theta is from 0 to pi by 2 and phi is 0 to 2 pi. It is also shown in this figure. Find a beam solid angle, exact and approximate, maximum directivity exact. The half power point of the pattern occurs at theta equal to 32.765. How do we do that? We again said this to be maximum is B naught. So B naught over 2 happens when? So we understand, so cosine to the power 4 theta is equal to B naught by 2, so 2. Okay, so thus the beam width in the theta direction is 65.53, twice of this value. So theta 1r is given by 1.1437 radians, and the beam width for the other plane is also given by theta 2r is 1.1437 radians. So beam solid angle omega A is given by integral of cosine to the power 4 d omega, and that is 2 pi by 5 steradians. And the approximate ones, by following this expression, omega is equal to theta 1r, theta 2r is given by 1.308 steradians. So 2 pi by 5 radian and 1.308 radian. Directivity is 4 pi by omega A is 10 dB, and approximate is 9.83 dB. So the exact maximum directivity is 10 and approximate value is 9.83 in this 9.681 is dimensionless. Yeah, so for in dB it is 9.83. So this even better approximations can be obtained if patterns have much narrower beam widths. So with narrower beam width, this approximation of the solid angle actually works better. That's what is demonstrated here. We go to the next one, another illustrative problem where this U is given by B naught sine cube theta. The input impedance of 73 ohms connected to a transmission line whose characteristic impedance is 750 ohms. And assuming the U is given by B0 sine cube theta, find the maximum realized gain of this antenna. So U max is nothing but B naught, and P radian is given by B naught 3 pi square by 4. So we calculate this too, we put it into the formula of D naught, which is 1.697. Then what we do is we assume an efficiency, radiation efficiency of equal to 1 because it is lossless, and then calculate the gain G0 as there is ECD times D naught, so it is exactly equal to 1.697, and in dB it becomes 2.297. So their directivity and the gain are identical because the radiation efficiency is 100%. There is another loss factor which is not taken into account in the gain, that is the loss due to reflection and mismatch. Okay, and that is equal to reflection mismatch is equal to 1 minus gamma square, and gamma square is nothing but Z in by Z characteristics and over Z in plus Z characteristics. So this 2 becomes 73 minus 50 and 73 plus 50. This is equal to 0.965. So the mismatch loss is equal to minus 0.155 dB. Okay. So the overall efficiency, even though the CD is considered to be 100%, but this ER contributes to that, hence it little bit less than the previous one. So we consider that 0.965 into 1.697, and we get that the more realistic gain to be 1.6376 or 2.142 dB. Okay, as compared to the previous 2.297. The gain in dB also can be obtained by converting the directivity and the radiation efficiency in dB and then by simply adding them. That also can be done. Okay. The question number 9. In this we are assuming a linearly polarized electromagnetic wave given by EI as E0 times e to the power minus jkz in the direction of x is incident upon a linearly polarized antenna whose electric field polarization is expressed by EA as AX unit vector plus AY times E function of r, theta and phi. Find the polarization loss factor. So incident wave is along x, and for the antenna the radiation pattern is along x and y. So the polarization loss factor is given by rho w dot rho a whole square, and that is given by this. So PLF in dB is 10 log 10 PLF in linear scale, which is given as minus 3 dB loss. Okay, so this is about how much is it? This is about 0.5, and in dB it is 0.5 log 10 times of that is essentially minus 3. Question number 10. A resonant half wavelength dipole is made out of copper where conductivity is given by 5.7 10 to the power 7. Determine the conduction dielectric efficiency of dipole antenna at frequency of 100 megahertz if the radius of the wire is 3 times 10 to the power minus 4 lambda and radiation resistance of the lambda by 2 dipole is 73 ohm. So at frequency of 10 to the power 8 hertz or 100 megahertz, we have lambda is equal to 3 meter and L is equal to 3 by 2 meter. So the C or 2 pi times B is 6 pi 10 to the power minus 4 lambda. For RL is half of the R high frequency, and so it is given by the formula RL equal to 0.35 or 0.349 ohms. So the the dielectric efficiency is given by 73 divided by 73 plus 0.39, which is about 99.52% efficient, and dB loss is given by minus 0.02 dB. Question number 11. A uniform plane wave is incident upon a very short lossless dipole where the length is less than the lambda is shown in the figure. Find the maximum effective area assuming that the radiation resistance of the dipole is 8T times pi L over lambda square and the incident field is linearly polarized along the axis of the dipole. So for the maximum effective area by the maximum power transfer theorem gives you this Vt square over 8 Wi times Rr. Since dipole is very short, the Vt is equals to E times L, and that gives you the incident power density is E square over 2 eta, and then the effective area is equal to EL square over this denominator, giving to 3 pi lambda square over 8 pi or 0.119 lambda square. So that brings us to a close of this particular lecture. There were quite extensive discussion on the solved problems. Please go through that. It has to be noted that we haven't created this content out of from the vacuum, so we have referred to the standard books. Particularly for this particular week, we are referring mostly to the Balanis and the Krauss's books, and so they are taken for this from these references mostly. I hope you have enjoyed this particular lecture and got something useful out of it. Please go through the problems because they are linked also to the assignment from this particular week. So see you in the next class. Thanks for joining.